going through some IB complex number questions so that you have an idea of how they work. What we're going to do is I'm going to go through the question and I'm going to show you the mark scheme. And then if there's something that needs to be further explained, I will just kind of mention that as we go through it. And I'll show you that if need be. So I'm going to show you the question and then I'm going to show you the mark scheme. And as we do that, hopefully you'll get an idea of some of the just patterns that are there, some of the things that could be showing up on an IB exam because they show up here quite often. And so I'm going through 2023 papers, 2022 papers, and a 2021 paper, and just looking at all the questions that we've done. So hopefully that will help. I'm going to share my screen and I'll show you the first one, and then we'll kind of go from there. So the first question says this: consider this polynomial. I'll zoom in a little bit. And it tells you a couple things, and these things are important. So Z is a complex number. That's important. And M belongs to the real positive numbers. So it says, given that Z minus 3i is a factor, find the roots of P of Z equals 0. So the first thing that you're going to recognize is the difference between a factor and a root. And if you look at the mark scheme, it just says 3i is a root, other complex number is minus 3i. So what does that mean, or where they're getting that from? What they're telling you is that Z minus 3i times something is equal to that polynomial of X. So if you jump back here, I think it's P of Z, sorry, not P of X. So if it's a factor, that means that when we go to set that equal to 0, that is a solution. So the solution to this being equal to 0 is that Z is equal to 3i. And because of that, excuse me, we know that conjugate roots happen in pairs. So Z equals minus 3i has to also be a root. So that's where they're getting that from. And that's something that's important to recognize, that if something is a factor, then the solution to it equaling 0 is the root, which I think you know, but it's just good to point out. And then also that these roots come in conjugate pairs. So if you look at the first step here, we're just recognizing two of the roots are 3i and minus 3i. So if that is the case, knowing those two things are the case, then we can plug those values in, knowing that the polynomial is going to equal 0. So that is where they're getting these statements here, that 4m minus 3mi plus 36 over m3i squared minus 3i cubed is equal to 0, because that's the function here, 4m minus m times z. So we're putting in 3i there, plus 36 over m3i squared minus 31, or 3i, sorry, cubed. So if you sort of work that down, there's two parts to this. And that is true of any complex number. And that's very important because that gives you really the opportunity to have a 2 by 2 system of equations. You have two equations with two unknowns. So in this case, we have two equations. We have the real part, which is these two pieces. So this one and this one. And then we have the imaginary part, which is this one, the stuff with I on it, so 27 and minus 3m. You can look at either of those to recognize that they have to be 0, so they have to be equal. So if 3m is equal to 27, then m is equal to 9. And then same thing here, 36 times 9 divided by m. You'll end up with the same answer. So eventually you'll get down to the fact that m is 9. And there's a bunch of different methods here. That's why there's more stuff. So you'll see the word over a bunch of times. But the simplest way is just to say 27 minus 3m equals 0. If I just grab that. So if I know 27 minus 3m is equal to 0, that means 27 is equal to 3m. And that means that if we divide by 3, we get m to be 9. So once you know that m is 9, now you can write out your equation, because the question asks you to find all the roots. And whenever you have a cubic, you have three roots. So we know that it's z minus 3i times z plus 3i, and then it's plus some other root. And that has to equal our polynomial in terms of z. So we know that that's what we're looking for. We're looking for that third root. Okay. So if you look at once you've got m to be 9, so we're going to kind of skip through some of these because you don't need to do all of them. You'll get down to the fact that m is equal to 9. And if m is equal to 9, and you know the roots, then you can basically solve for the third root by saying, if you look at this, z minus 3i times z plus 3i times r minus z has to equal our polynomial that we have. And if you go back here, and with m equal to 9, it's kind of probably helpful to do that just to show you. So I'm going to go 4 times m, so 4 times 9, and then it's minus m times z, so minus 9 times z, and then plus 36 divided by m, so plus 36 divided by 9 times z, leave it squared, and then minus z cubed. So 4 times 9 minus 9z plus 4z squared minus z cubed. That's my polynomial. And when I set that equal to 0, what I'm going to get is r, or z minus 3i and z plus 3i I know. And then it's going to be z minus r, some other value of the root that has to equal 0. So what happens is if you look at the kind of statements here, that this is how it's split. If I multiply this, I'm going to get z squared, and then minus 3i and plus 3i. These are a conjugate pair, so we know that they're just going to come out to minus 3i times 3i, which is 9i squared, so it's going to become plus 9, and then times z minus r, and that has to equal 0. So if I look at that, and I multiply it out, then I get z cubed minus r times z squared plus 9z minus r times 9, or 9r, has to equal 0. And if I look up here, this is what I'm supposed to have. So if I look at what then r is required to be in order for that to work, it's got to be 9. So I can see, or sorry, it's got to be 4 from that z squared, and also from the fact that it's 9 times r is going to give me that. So I'm going to get r to be 4. Okay. Now it's minus, and that's plus, and this is minus, and that's plus. So you essentially get z minus r becomes z minus 4. So r is 4. So my fourth root is 4. So if you look at the Mark scheme, whoops, that's not the right thing to click on, sorry. You will see that that's my third root is 4. And again, I'm finding a root, not a factor. So the factor is z minus 4, and that gives me a root of positive 4, or 4 minus z here. So you can see those are my 3 roots, and hopefully that makes sense. So that's the first question. And if there are any other questions, obviously you can follow up with me afterwards. The second question, and this is another one that we looked at before, says this: consider this complex number, u, which is minus 1 plus 3i. And it says, first of all, by finding the modulus in the argument of u, show that u is 2i, or 2ei to the 2 pi over 3. So to find the modulus, you just take the square of the two values, so a squared plus b squared. So that gives you square root of 1 plus 3, which is 4, so you get 2. And then if you take the arctan, and this is something to watch for as well, because if you look at the modulus and the argument, your modulus is always positive because it's always this. It's a squared plus b squared. So it's not really an issue. But when you get to this arctan of b over a, you have to be careful with that. So if I have, in this case, minus 1 plus root 3i, minus 1 plus root 3i gives me an a value of minus 1 and a b value of root 3. So to find the modulus, you just take the square root of minus 1 squared plus root 3 squared. That's easy because that just gives you 1 plus 3. That's the square root of 4, which is 2. So that's not too bad. And relatively straightforward application of the formula. When you do the theta, you're taking the arctan, and you can do this a couple of ways. So you can either do it as b over a as root 3 over 1, leaving out the negative, or I can put the negative in. The issue with the negative is only where are you? What quadrant are you in? So if you think about the real part's negative and the imaginary part's positive, you're over here. You're in the second quadrant. So the arctan of root 3 without the negative is pi over 3. So that's my reference angle. And that's just from our special angles, or our special triangles. But we're in the second quadrant. So now the reference angle has to then be translated into the angle in the second quadrant, which is 2 pi over 3. So that's how you get there. It's not always well explained in the mark scheme. So if you look at the mark scheme here, it just says the reference angle is pi over 3, and then it's pi minus, or it's pi plus the arctan of minus 3. All they're saying is you have to make sure you're in the right quadrant. Okay. So that's how we get the modulus in the argument. And once you have that, you have it as it is here. So that's what you're trying to prove. So part B says find the smallest positive integer n such that un is a real number. So if it's a real number, what does that mean? Well, what that means is your complex part, the part that has I in it, has to be 0. So if you look at the statement here, the mark scheme here, it says the start that un belongs to real numbers means that 2n pi over 3 is equal to k pi. Okay, so it's like, well, why is that the case? And the reason that that's the case is if you take any complex number, now we have it written in Euler's form right now, but if I was to write it in polar form, it's r cis theta. So in our case, it's 2 cis of 2 pi over 3. And if you think about, we want the real part, so the real part's the cosine of 2 pi over 3. We want that to be a number, but we want this part to be 0. So if I expand this, this is my number. So let's call it Z for a second, or I guess it's called U. So we'll use U. So then if I raise that to a power, U to the N becomes R to the N, and then cosine of 2 pi N over 3 plus I sine of 2 pi N over 3. And that's using de Moivre's theorem. So when I know that, what I need this to be 0. And the sine of that being 0 is only going to happen at either 0 or pi, because the sine of 0 is 0 and the sine of pi is also 0. So that is where we're getting this statement that it has to be some multiple of pi, where k belongs to the integer. So either 0, because 0 times pi is 0, or something bigger than that, but it has to end up being a multiple of pi. So in order for that to happen, if I want 2 pi n over 3 to equal some multiple of pi, so let's say k pi, then I have to just recognize that I need to get rid of that fraction. And in order to get rid of that fraction, I have to multiply it by 3. So my n value is going to be 3. That's the smallest value, because that will then give me 2 pi, and I'll be able to get a 0 value for sine. So that's where they're getting n equals 3. Okay, the second part of this then says find the value of un when n takes that value. So now what we're doing is we're plugging in that 2 pi, taking the cosine of 2 pi, and multiplying it by 2 cubed. And that comes from this part of my complex number. So I'm just now in that second part saying, okay, if I jump down here, what is cosine of 2 pi times 3 divided by 3, and then times 2 cubed? Because our R value is 2 from the previous question, the previous part of the question. So that gives me 8, and then cosine of 2 pi, and the cosine of 2 pi is 1, and so we get 8 times 1, which is 8. So that's where they're getting that part from. So hopefully that makes sense. And then we're moving on to part C. Part C says here's a function, z cubed plus 5z squared, plus 10z plus 12 equals 0. And it says given that u is a root, find the other root. So it's very similar to the previous question. So I'm not going to do this one in as much detail, but I know that one of the roots is this because it says it is. which means the conjugate has to also be a root of that. So that's where we're getting this statement, okay? And so we have to then take those two values and find the third one. And if you look at what the question says, if you know two of the roots and it's a cubic, there has to be one more. There has to be one more root. And so we're going to try to find that root. So you can see either you add the roots up to get your value. The sum of the roots has to be the second term's coefficient. That's where that -5 is coming from. It's coming from here. Okay. Or you can use the product of the roots has to be the last number, which is this guy. Okay. And again, you're switching sign because it's a root, not a factor. So the factors have to multiply to give you 12. Therefore, the roots have to multiply to give you -12. Okay. So either way, you're going to end up with a C value that's -3. Okay. And if you look back up here, it says consider this equation where Z is a complex number. Given that U is a root of this, find the other roots. It doesn't necessarily imply that there's one real root and two complex roots, but because there's complex roots come in conjugate pairs, there's two complex roots. Then that third one has to be real because otherwise we would have a fourth one. In other words, it doesn't have a conjugate pair. So that is why if you look at the Marx scheme, they're saying, let C be the real root. Like, how do you know there's a real root? Well, you know that because conjugate of a real root is the same as itself. So anytime there's three roots, one of the roots is either is real or is complex without that complex part or without that real part. So that's how we know that it's the real root. And we know it's a real root because it doesn't have that conjugate pair. So hopefully that makes sense. Again, if you have any questions about that, please feel free to follow up later. So then the next part of the question says, now you know that, you know those roots. It says by using a suitable transformation from Z to W or otherwise find the roots of the equation 1 + 5W plus so on. So what you'll notice is in this, the numbers are exactly the same as this. The coefficients are. All that's changed is that the biggest number, so Z cubed, I guess not the biggest number, but the biggest power, is now gone. And all the powers have essentially reverted. So they went from Z cubed, Z squared, Z to nothing, now to 1. So 0 for the power, to 1, to 2, to 3. So what has happened there is essentially this. This is what it means by a suitable transformation. So if I have Z cubed, Z squared, Z, and then nothing, and I have nothing, and then W, and then W squared, and then W cubed, what have I done? Well, if you look at basically what I've done is I've said, okay, I'm just flipping the power. So I'm essentially taking this and dividing it by Z cubed. Okay, because Z cubed divided by Z cubed is Z cubed over Z cubed, which is just 1. It's Z to the 0. Z squared over Z cubed just gives me 1 over Z. Z divided by Z cubed gives me 1 over Z squared. And then nothing, so a number divided by W cubed, divided by Z cubed, leaves you with a number divided by Z cubed on the bottom. So you'll notice what essentially has happened is that now I have all the powers, but they're negative. So if I let W be 1 over Z, then this becomes W, this becomes W squared, and this becomes W cubed. So all we're doing is flipping them. So that's the transformation. And if you look at the Marx scheme, that's what it says, that Z is 1 over W or W is 1 over Z. When you've done that, well, now that you know that, it says find the roots of the equation. So essentially all we've done is taken the roots at Z values, we just flip them as well. So you'll notice that all of our roots now are just inverses. So our roots were these, and now they're these, okay? So there's other ways to do it that shows you those things, but really the easiest way to do it is to see that transformation. And then this one says, consider the equation z squared is equal to 2z star. So z star is the conjugate of z. So it says, by expressing z in the form a plus bi, find the roots of the equation. So all we're going to do is say, what is a plus bi squared? And then what is 2 times a minus bi, because that's the conjugate of z. So we just expand that. A plus bi squared is a squared plus 2abi plus bi squared, right? Which is where this is becoming a minus b squared. So just to clarify that, because again, sometimes the mark scheme, it skips a step. So I have a plus bi and I'm squaring it. Using the perfect square, I know that it's the first term squared plus 2 times the product of the terms plus the second term squared. What is happening though, because of that I, this is staying, but that I squared is going to make this minus 1. So it becomes minus b squared. So that's where that's coming from in right here. So that's where that part comes from. And then it's just 2a times minus 2bi. So what it says is those things are equal. So that means the real part has to be equal to the real part. So again, the real part here is 2a and the real part here is a squared minus b squared. So that's where we're getting this statement. And then the conjugate part has, or sorry, the imaginary part has to be the same. So 2ab has to equal minus 2b. And if you just solve that equation, you will get basically solve it by substitution or solve it by elimination. But if you factor this or this, I guess, first, they're taking 2b out, saying 2b times a plus 1 is equal to 0, which either means b is 0, so a is 2, or a is minus 1, which means b is plus or minus root 3. And so you end up with minus 1 plus root 3i and minus 1 minus root 3i, and then 2. Those are your 3 options. So hopefully that makes sense. And that's the last part of that question. Now that's a big one. That's 22 marks, so it's a lot. But hopefully, that helps in terms of understanding. So then we have this question. And this question says that here's my function. Well, not really function, but complex number, but it's a function of cosine and sine of 11 pi over 18. Excuse me. And it says find the smallest value of n that satisfies that z to the n is equal to minus I. So what that tells you is, first of all, the real part has to be 0. So if you look at the mark scheme, what we're noticing is that if you use n to a power, you're using Moyer's theorem, you get this. You get cosine of 11 pi n over I sine of 11 pi over 18. So you have those two separate things. Then you say, okay, well, I need the second part of that, the complex part of that, to be 0. Right? So I have to have that 11 pi over 18 come into something that is going to give me 0 when I take the sine of it. And as we discussed previously in one of the questions before, sine is 0 when you're taking the sine of 0 or 2 pi times that. Like if you add 2 pi, so any multiple of 2 pi from 0, or when it's pi, right? And then if you want it to be -1 or +1, then it's at pi over 2 or 3 pi over 2. So we have to look at what we're gunning for. What we're gunning for right now is minus I, which means our sine of 11 pi over 18, this part, times n. So this sine of, sorry, I can't just grab that. But this part here, sine of 11 pi n over 18, has to equal -1. So I look and say, okay, well, what value of n is going to let me do that? And it has to be a multiple of 3 pi over 2. I have to get to 3 pi over 2. Or some multiple of 3 pi over 2, because 3 pi over 2, the sine of 3 pi over 2 is -1. And that is because of our unit circle. So you say, okay, well then I need to either be 3 pi over 2 or some multiple of that. So it can be 7 pi over 2 or 11 pi over 2. It just has to be a full circle. So it has to get to 1 full rotation plus that, or 2 full rotations plus that, or whatever. So we're gonna look at the smallest one, which means it needs to be 3 pi over 2. In order for it to be 3 pi over 2, then I just have to basically make 11 pi n over 18 equal to 3 pi over 2. So if I take that, just that statement, just to show you, if I take 11 pi n over 18 and set it equal to 3 pi over 2, then the pi's are going to cancel. Okay. And then I get, if I bring that 18 up, I'm just going to get 11n is equal to 3 times 18 divided by 2. And then you can solve that by 18 divided by 2 is 9. So 11n has to equal 27. And then you can kind of go to n is right here. You can see 11 n over 20, 11n equals 27. Now you might be saying, okay, well, how did 11n over 27 become 9? Because 27 divided by 11 is not 9. So how did that happen? What you need to think about is I need n to be a whole number, right? So I can't let n be just 27 over 11. That doesn't work. So I need it to be some multiple of that. So if n is 9, I need to essentially get that, if n is 9, to 11 pi over 2. Now, 11 pi over 2 is not 3 pi over 2, sorry. But if you take 8 pi over 2 away to get to that 3 pi over 2, 8 pi over 2, if I focus in on that for a second, is just 4 pi, which is actually a multiple of 2 pi. So in other words, 11 pi is going to get me to 3 pi over 2. 11 pi over 2 is the same thing as 3 pi over 2. So if n is 9, it works. All right. It's not that if you solve this, that 11 pi or 11n over equals 27 means n equals 9. It's the fact that you're going a full rotation. So it's the same place if n is 9. So hopefully that makes sense, because that's the other thing in the Marx scheme. You say, well, 11n over 27, how does that translate to n being 9? It translates that because it has to be some multiple of that. And if you look at the Marx scheme, it does kind of say that, right? You can sort of see it's either 27 or 63 or 99. 27 is not divisible by 11. 63 is not divisible by 11. So that's where 99 divided by 11 actually gives you 9. So you're not getting a whole number answer until you get to that third one. So hopefully that makes sense. It's just we're looking at all the possibilities. I'm zoning in on the first one here just to show you how we're getting to 27. But 27 doesn't work. 27 divided by 11 is not 9. It's not a whole number, though. So we go to the next one, which would have been 7 pi over 2. Because you're adding 4 pi over 2 or 2 pi each time. So that 7 doesn't work either, because you get 63, and 63 is not divisible by 11. So that's how you have to get to 9. So you need the minimum value. So hopefully that clarifies that part of it. So then it says, hence or otherwise, describe a single geometric transformation applied to Z on the Argon diagram that results in Z to the 10. So what we want to recognize is, it says hence or otherwise. And again, whenever you're doing an IB question where it says hence or otherwise, the hence is kind of important. So if I want Z to the 10, I can recognize that that is Z to the 9 times Z. All right. And Z to the 9, we already said was minus 1, minus I. So if you look at the Marx scheme, you can kind of recognize that fairly quickly, that the argument of Z to the 10 and the argument of Z is needed, because argument of Z to the 10 minus argument of Z is Z to the 9. All right. So recognizing this is what I'm saying. Okay. Now, when you multiply, what do you do to the angles? You add the angles together. So you have Z to the 9 times Z. The argument for Z to the 9 is 11 pi over 2. And then you're adding in, if you look at our values, we have 11 pi over 2 here. And we're adding to our angle, the angle of 3 pi over 2, because that's the one for Z. So if we jump back to the question for a second, Z is this, right? So we're taking, let me just write this out a little bit better for you. So Z to the 9, we said that our angle is going to become 3 pi over 2. Sorry, 11 pi over 2 for Z to the 9. And then we're going to add to that, and this is just the argument. We're just talking about theta. We're going to add to that our 11 pi over 18. Okay, because that's the argument for z. So z has that as an argument, 11 pi over 18, and z to the 9 has 11 pi over 2. So if you add them together, right, a pi over 2 clockwise or 11 pi over 2 or that, you'll see all this. If you just take our angle and we add 11 pi over 2, which is what we're saying, okay, then you will get to where you want to go. Now, 11 pi over 2 can be reduced. That's why we're saying a rotation. You'll see a rotation of 3 pi over 2. We already talked about that it can get back down to 3 pi over 2, but they will accept 11 pi over 2. So we're just going around because we're adding to that angle because of de Moivre's theorem. We multiply, we're allowed to just add the angles together. So there's a lot of stuff in this mark scheme in terms of like this or this or this, but really all we're doing is saying we're just adding the arguments together. The argument is 11 pi over 18, and we're adding 11 pi over 2. So we're just going that rotation. Okay. So hopefully that makes sense to you in that last part. So that one, again, it's only 7 marks. It's not a lot of time, but it is something to kind of be aware of in terms of, again, the use of de Moivre's theorem. So if you look through all of them so far, you're asked to find roots and factors. That's what this question was. You're asked to find roots and factors again here, but also switch something and find a power. And then here, you're asked to just find a power or show the value of n. So a lot of it has to do with the same types of questions. You're either asked to find a power, you're asked to find a root, or you're asked to do some sort of operation with complex numbers. Okay, so here's another question. This one is a little bit different because this does not have things in polar coordinates right now. So it says the complex numbers are 1 plus bi and 1 minus b squared minus 2bi. So I don't have them in polar coordinates, and I'm probably not going to right now. When it says to find the expression for z1 and z2 in terms of b, I'm just going to multiply them together. So this is slightly different, but still kind of important in terms of knowing how to work with things like this, because what you're going to do sometimes is you're going to have to make a decision about, I don't know why, sorry, there's something in the way of my values to jump to the mark scheme. So actually, I'm going to close these tabs out. So what you're going to do is you're going to have to make a decision to finish my thought between how do you know when I'm supposed to switch from rectangular to polar or to Euler's method or stay in rectangular. So because these are, it's just a Z1 times Z2, and because it's all rectangular already, I'm just going to multiply them. So to save you the pain of watching me actually multiply them, you can see that's what we're doing here. So 1 plus bi times 1 minus b squared minus 2bi, and you just expand it. And what you end up with, if I zoom in, is this. So it's really, at this point, just algebra. Now, the question then says, once you have that, hence, given that the argument z1, z2 is equal to pi over 4, find the value of b. So now we've switched to polar, but if the argument, if theta is pi over 4, then what you know is if theta is pi over 4 and is the arctan of b over a, what that necessarily implies is that b over a has to equal 1, because the tangent of pi over 4 is 1. Okay, now b and a, not the b that is in this question right now, right? But just any coefficient. So when I look at my statement, and again, sorry that when I'm sharing my screen, sometimes it pops up this thing and it gets in my way. So that's why I'm finicky with this. But if you look at the value of b here, we just found the complex part and the real part in rectangular coordinates. So what we're going to do with that information is we're just going to say that they have to be b over a. So the imaginary part, which is minus b cubed, over the real part, which is 1 plus b squared, that has to be 1. All right. So if minus b cubed over 1 plus b squared is 1, then if I take out a minus b squared out of this minus b cubed, I get b. Sorry, if I take out a minus b, I can't take out a minus b squared. If I take a minus b out, I get 1 here plus b squared left. So I have minus b into 1 plus b squared divided by 1 plus b squared, right? And what that tells me then, if you look at what they did here, is they just said, well, then the arctan of minus b has to be pi over 4, so b has to be minus 1. So they're simplifying first, I'm simplifying after, but essentially these are going to cancel, and I just get this to be 1, so that means b is minus 1. The reason I can cancel those, and this is important to recognize, is because back here, it says b is not allowed to be 0, and it has to be a real number. So those are important statements. When I look at this statement here, I'm saying 1 plus b squared is not allowed to be 0 because b belongs to real numbers. All right. And 1 plus b squared is a real number. So in other words, if that's 0, then I'll have only a complex part. I'm not going to have a real part. And I need to have a real part because of this. Okay, so that's the sort of little stipulation there that prevents that problem from happening, because otherwise we would say, well, then we can't just divide by that because we could be dividing by 0, but we're not allowed to divide by that being 0 because it can't be 0 because b is a real number. So 1 plus b squared can't be 0, because if you're taking 1 and adding a real number that's squared, you have to get a further real number. So hopefully that one makes sense. So we've gone through quite a few. I'm going to keep going through them, but that one just gives you a little bit of another nuance, same kind of idea, but just a little different nuance to it. So then we run into this one. This one is much longer or much bigger. We did do this one in class. And so I'm going to quickly go through this one a little bit more quickly. But what it tells you is, here's my 3 pieces of information that it gives me. It says that Z1, O, and Z2 are the vertices of a triangle. So Z1 is some complex number. You will notice it has an R value. We don't know what it is. And it has an angle, and it's alpha. Z2 has an R value. We don't know what it is. And it has an angle theta. So the argument of Z1 is alpha. The argument of Z2 is theta. So it says that these points represent these complex numbers. But it does tell us some information. It says that R1 and R2 are positive. They're bigger than 0. And that alpha and theta are between 0 and 2 pi, and that alpha is always bigger than theta. So the first part says, show that Z1 times Z2 conjugate is this. And so you have to just take into account that the conjugate of the second one is just minus in Euler's form, it's minus the power. So it switches. So if you look at it, it's R1 EI alpha and R2 EI theta. If you take the conjugate, you just change the angle to a negative. So that's where that is coming from. And then if you're multiplying, you multiply the R values together, and then you you add the angles, but because one of the angles is negative, you get alpha minus theta. So that's where that first part comes from. Then it says, given that the real part is 0. So this is another example. This happens fairly regularly, where the real part is given and that real part is 0. Or sometimes it will say the complex part is 0. But if the real part is 0, what I have to look for is say, okay, well, if you write it in polar form, not in Euler's form or Euler's form, you get this, right? It's cis of theta. Theta, in this case, is alpha minus theta. So you're saying that the real part, so the cosine of that has to be 0. The only way that cosine of that is 0 is if theta is pi over 2. The angle, not the theta here, but cosine of an angle being 0 means the cosine has to be pi over 2, or some multiple of that. And so that means that the argument here, which is alpha minus theta, has to be a right angle. It has to be 90 degrees or pi over 2 radians. So it's a right angle triangle. So that's the first part. And I think that's relatively understandable. The second part says, in part C, D, and E, consider the case where that's an equilateral triangle. So now the angle has changed, and the angle in here then, alpha minus theta, is now equilateral, means it's pi over 3. Okay, so that's important. You got to read that. So if you look at what it asks you to do, it says express Z1 in terms of Z2. So Z1 is equal to this theta plus this angle. So it's this theta. So Z2 is theta. And then we're adding pi over 3, and that will get us to Z1. So that's where we're getting this. Okay. So Z1 is now Z2 times EI to the pi over 3, because we're taking the angle theta and we're adding pi over 3 to it to get alpha minus theta, or to get alpha. So that's just recognizing that the angle here in this diagram right here, that's now pi over 3. So Z2 times, or adding that pi over 3 is going to give me Z1. So hopefully that part makes sense, just sort of reasoning it. Then it says, hence show that this is true. So all you have to do is take what is Z1 squared, what is Z2 squared, and what is Z1 times Z2. So that's all we're doing. We're just plugging in and trying to figure out what that equals. So we're going to say, well, Z1 is this. So Z squared plus Z2 squared, Z1 squared plus Z2 squared is Z2 squared e to the I, excuse me, 2 pi over 3. The 2 coming from the fact that De Moivre's theorem says multiply the angle by the power, and the power is 2 plus Z squared. And then if you look at the other side of that, you're trying to show that it's Z1 plus Z, or Z1 times Z2, and you already know what Z1 times Z2 is from looking at Z1 is Z2 times this. So Z2 times that is just Z2 squared e to the I pi over 3. So you kind of show there's our Z2 squared. So we just need this to be I to the pi over 3. And when you see this, you might say, well, how do you know that e to I to the 2 pi over 3 plus 1 is e to the I pi over 3? What is that? How do you know that? Well, if you think about 1, that's e to the I times 0. And so that's where you're, if you kind of look at the 1 is going to give you the cosine I sine has to be then that the imaginary part has to be 0. So I'll just show you what I'm kind of saying with in terms of cosine and sine. So a lot of complex number stuff, it has to do with sine and cosine. So I have e to the 2 pi over 3 times I plus 1. And 1 is really, I can write as e I to the 0 because e to the 0 is 1. And so then if you kind of think about this in terms of sine, you need to, well, let me even just make it easier for you to think about that's a real number, right? So the complex number part has to become the same. And so sine of 2 pi over 3 I has to equal the sine of the new angle. And the new angle is just pi over 3i because they're the same in terms of where the quadrants are. So you can look at it that way, and I think that's probably the easiest way to recognize it, is that sine in the first quadrant, sine in the second quadrant. But the same, the other way of looking at it is this, that if you have 2 pi over 3, which is here, then this is just pi over 3 here. And so you're going to end up down here if you add pi over 3 to it. So either way, sort of geometrically or that way, it makes sense that that is equivalent. Now, if you don't get that or don't like that, you can say that or this. So this is the real and imaginary parts of this number. So EI to the 2 pi over 3. And then we're adding 1. So that's putting us to here. And then if we work our way backwards, that is pi over 3. So if you go back to your arctan, is now arctan of root 3 over 1. So that, I think, hopefully helps you see it as well. If you want to do it that way, it does take a little bit longer. So either you look at it geometrically, sort of with the trig, or you can actually put it into rectangular coordinates and solve it. And I'm trying to go through this quickly. That's why I'm not writing everything down. But you basically get your answer. And I think that's when it says show, you basically have to get to the point where you have something on one side that's equal to something on the other. So you start on the left-hand side and go all the way down to the right-hand side. And then part D says, okay, Z1 and Z2 are the distinct roots of this equation. Use the results. Part C2, show that a squared minus 3b is equal to 0. So what you're doing is saying, well, Z1 plus Z2 is minus a, and Z1, Z2 is b. So, and if you look at where that's coming from the polynomial. That if you're adding the roots together, it has to be minus that coefficient, and if you're multiplying them, it has to be minus that coefficient. Okay, if you're talking about the roots. If you're talking about the factors, then it's just those values. So Z1 times Z2 is b, because they're the two roots. And then you can solve it by saying, okay, well, if Z1 plus Z2 is minus a, then if I square that, I get this. So Z1 squared plus Z2 squared plus 2, Z1, Z2. And then Z1 squared plus Z2 squared uses the result. So it's important when it says use the results, what it's saying is you got to use this little theorem that you just proved. So I know Z1 squared plus Z2 squared is Z1, Z2. So I'm going to take this that popped out, Z1 squared plus Z2 squared, and make it Z1, Z2. And then that gives us 3, Z1, Z2. So given that B is Z1, Z2, we put the B in for that, and we get 3B. So A squared is equal to 3B. And so a squared minus 3b is equal to 0. And there's another method that's kind of the same that you can see there, but so then the last part says, now consider this equation. So now it told us b is 12. And it says, given that this is true, deduce the only equilateral triangle that can be formed. So all we have to do is say, okay, well, if b is 12, then a squared minus 3 times 12 has to equal 0, which means a is plus or minus 6. Then we plug that in, saying, okay, well, if a is minus 6, then Z1 is 3 plus root 3i, Z2 is 3 minus root 3i, and alpha minus theta is minus 5 pi over 3. So we're just plugging that into our equation up a ways here for Z1 and Z2. It's not showing the mark scheme, but you're basically just going back up to where we had A and B. We're showing this is true, so then we're getting this equation. What you end up with in that regard is that angle can't be negative. It doesn't put us in that alpha minus theta equaling 0 to pi. And the only other option then is that A is 6. And if A is 6, then you get alpha minus theta to be pi over 3, and it is equilateral. And so therefore that has to be your answer. So that's also a long one. We did that one in class just a few days ago, so I didn't spend as much time on that one, but obviously we can go through that if you want in more detail. Please just feel free to reach out anytime. Given the length of this video is now almost to an hour, I'm just going to quickly remind you of these two questions as well. We're not going to go through them in detail. I just want to point out some things that when you read a question, you should know. So this says, consider this quartic equation. If it's a quartic equation that tells you that there are 4 roots, right? 4 total, it gives you 2 of them. It says one of the roots is a plus bi and the other is b plus ai. So what you know is you actually, because you know 2 of them, you actually know 4 of them, because the other ones are a minus bi and b minus ai. They're the conjugates. So you see there, the other 2 roots are the conjugates. And then what you need to recognize, and we talked about this before, but the sum of the roots is the coefficient there, all right, but negative. And the product of the roots is this last number, which is 400. So then you set up 2 equations. So the roots, if you add them up, have to give you minus 4. And so if you reduce the roots, when you add them together, the i's cancel. So you get 2a plus 2b is equal to minus 4. And then if you multiply them, if you expand them out, you get this. And so what you end up with is the ability to solve the question. And it's not that difficult afterwards. So we're not going to go through that in great detail, except to say you have to recognize when they always occur in conjugate pairs. So that's that question. And then this one, when you look at the question that starts in polar form, then you generally want to do the question in polar form. So it says find the modulus of ZW. When you multiply two complex numbers in polar form, the modulus is just the product of the two. So it's 2 times 8, and you'll see that here. Okay, and then the argument is just this plus that. Okay, so you add them together. So pi over 5 plus minus 2 pi k over 5 is equal to 1 minus 2k pi over 5. So you're just adding them together. The only thing to recognize is that when you have a plus in cosine and a minus in sine, that the angle or the modulus is negative because you're positive here and negative there. Okay, so whenever that happens, you know the angle's negative. So we have that. Then it says find the minute number of k. Suppose that it belongs to the integers. So what we have to do is say, okay, well then that angle, and this is where it comes back to your knowledge of trig. It has to be a multiple of pi because the cosine of pi is -1 and the sine of pi is 0. So you need to get that argument or that angle to give you just a real number. So that's where they're getting that 1 minus 2k has to be a multiple of 5 then, because we want that top part to divide by 5. And then you can solve for k to get k to be 3. And then the next part of the question, the last part of the question just says, okay, now that you've found that, what is the value of ZW? So you just plug in 16 for R and minus pi for your angle. So overall, and that's all the way through all the questions down to, I think 2021. And it's a long video, and I haven't been able to cover every question in very specific detail, but hopefully that helps you. And if it is engendering more questions than it is solutions, please feel free to reach out and see me. But hopefully that gives you an idea of how to do those questions and gives you an idea of the way that those questions are asked and what are the things that you have to do. So most of the time, you're either doing operations with complex numbers, you're adding, subtracting, multiplying, dividing them. You are doing that in rectangular coordinates some of the time, but mostly in polar coordinates. And you're also doing some algebra sometimes, but most of the time you're just multiplying, adding, subtracting, or dividing, or raising it to a power, and then you're finding roots. And you just got to remember those little things, like the roots always are always in conjugate pairs and things like that. And the more you do them, the more questions you do, the better off you will be in terms of recognizing those patterns. So I would encourage you to try some more of them, but hopefully that is helpful to you. I'm going to stop the video here. And if you have any other questions, please feel free to reach out.